Hello everyone, myself is Dinesh and my topic is apply properties of monoid with example. In abstract algebra, a branch of mathematics, a monoid is a set equipped with an associative binary operation and identity element. Monoids are semigroups with identity. Such algebraic structures occur in several branches of mathematics. For example, the functions from a set into itself form a monoid with respect to function composition. In abstract algebra, more generally, in category theory, the morphisms of an object to itself form a monoid, and conversely, a monoid may be viewed as a category with a single object. In computer science and computer programming, the set of strings built from a given set of characters is a free monoid. Transition monoids and syntactic monoids are used in describing finite state machines. Trans- Trace monoids and history monoids provide a foundation for process, calculi, and concurrent computing. In theoretical computer science, the study of monoids is fundamental for automata theory, Krohn-Roach theory, and formal language theories. Star height problem. A set S equipped with a binary operation S into S map into S, which will denote dot is a monoid if it satisfies the following two axioms. Associative for all a comma b and c in S, the equation a dot b of dot c equal to a dot of b dot c holds. Identity element. There exists an element E in S such that for every element A in S, the equations E dot A equal to A and A dot E equal to A hold. In other words, a monad is a semigroup with an identity element. It can also be thought of as a magma with associative and identity. The identity element of a monad is unique. For this reason, the identity is regarded as a constant, that is, zero array or null array expression. The monad therefore is characterized by specification of the triple s comma dot comma e. Depending on the context, the symbol for the binary operation may be omitted so that the operation is denoted by juxtaposition. For example, the monad axioms may be written AB of C, AB into C is equal to A of B into C, and EA is equal to AE is equal to E. This notation does not imply that it is numbers being multiplied. A monad in which each element has an inverse is a group. Submonoids. A submonad of a monoid m comma dot is a subset of n of m that is closed under the monad operation and contains the identity element E of m. Symbolically, n is a submonad of m if n belong m is n is if n is subset of m, comma x dot y belongs to n where x comma y belongs to n and E belongs to n. In this case, n is a monoid under the binary operation inherited from M. On other hand, if n is subset of monoid that is closed under the monad operation and is a monoid for this inherited operation, then n is not always a submonoid since the identity elements may differ. For example, the singleton set 0 is closed under multiplication and is not a submonoid of the multiplicative monad of the non-negative integers. Examples. Out of the 16 possible binary Boolean operators, each has a fold that has a two-sided identity, is also commutative and associative, and thus makes the set false, true a commutative monad. Under the standard definitions, and XNOR have the identity true, while XOR and OR have the identity false. The monads from AND or OR are also idempotent, while those from XOR and XOR are not. The set of natural numbers n is equal to 0, 1, 2, up to so on is a commutative monad under addition. Identity element 0 or multiplication and element 1. A submonad of n under addition is called a numerical monoid. The set of positive integers n by 0 is a commutative monad under multiplication identity element 1. Given a set A, the set of subsets of A is committed to monoid and the instruction and element is A itself. Given a set A, the subsets of A is a commutative monoid under union, excuse me, identity element is an empty set. Generally, generalizing the previous example, every boundary similarity is an idempotent commutative monoid. In particular, any boundary lattice can be endowed with both a meet and a joint monoid structure. The identity elements are the lattice top and its bottom, respectively. Being lattices, Hating algebras and Boolean algebras are endowed with these monoid structures. Every singleton set X closed under binary operation dot forms a trivial one element monoid, which is also the trivial group. Every group is a monoid, and every abelian group a commutative monoid. Any semigroup S may be turned into a monoid simply by adjoining an element E not in S and defining E dot S equal to S equal to S dot E for all S belong to S, capital S. This conversion of any semigroup to the monad is done by the free functor between the category of semigroups and the category of monoids. Thus, an idempotent monoid, sometimes known as find first, may be formed by adjoining an identity element E to the left zero semigroup or a set S, capital S. The opposite monoid, sometimes called find last, is formed from the right zero semigroup over capital S. Adjoin an identity E to the left zero semigroup with two elements LT, GT. Then the resulting idempotent monoid LT, E, GT models the lexicographical order of a sequence given the orders of its elements with E representing equality. The underlying set of any ring with addition or multiplication as the operation by definition, the ring has a multiplicative identity 1. The integers, rational numbers, real numbers, or complex numbers with addition or multiplication as operation. The set of all n by n matrices over a given ring with matrix addition or matrix multiplication as operation. Properties. The monad axioms imply that the identity element E is a unique if E and F are identity elements of a monad, then E is equal to E, F is equal to F. Products and powers. For each non-negative integer n, one can define the product Pn is equal to phi of n to I equal to 1 of any sequence A1 up to An of n elements of a monoid. Recursively, let P0 equal to E and let Pm is equal to Pm minus 1 dot Am for for 1 less than m less than or equal to n. As a special case, one can define non-negative integer powers of an element x of a monoid, that is, x naught equal to 1 and x power 0 equal to 1, x power n is equal to x power n minus 1 into x for n is greater than equal to 1, then x power n plus n equal to x power m into x power n for all m comma n greater than equal to 0. Invertible elements. An element x is called invertible if there exists an element y such that x dot y equal to e and y dot x equal to e. The element y is called inverse of x. Inverses, if they exist, are unique. If y and z are inverses of x, then by associative y equal to ey equal to zx into y equal to z of x into y equal to z equal to z. If x is invertible, say with inverse y, then one can define negative powers of x by setting x power minus n equal to y power n for each n less than or equal to 1. This makes the equation x power m plus n equal to x power m into x power n whole for all m comma n belongs to integers, that is z. The set of all invertible elements in a monoid together with the operation dot forms a group. Equational presentation. Monoids may be presentation much be in the same way that the groups can be specified by means of group presentation. One does this by specifying a set of generators sigma and a set of relations on the free monoid sigma star. One, one does this by extending finite binary relations on sigma star to monoid congruences and then constructing the quotient monoid as above. Given a binary relation, R is subset of sigma star into sigma star. One defines its symmetric closure as R union R inverse. This can be extended to a symmetric relation E subset of E star into E star by defining X belongs to E of I if and only if X is equal to SUT and Y is equal to SVT for some strings U, V, S, T belongs to sigma star. Let U, V belongs to R union R inverse. Finally, one takes the reflexive transitive closure of E, which is then a monad congruence. In the typical situation, the relation R is simply given as a set of equations so that R equal to U1 equal to V1 up to UN equal to Vn. Thus, for an example, P comma Q such that PQ equal to 1 is the equational presentation for the bicyclic monad, and A comma B such that A into B into A equal to B into A into A, comma B into B into A equal to B into A into B is a plactic monad of degree 2. It is finite order. Elements of this plactic monad may be written as for integers I, j, k as the relations show that BA commutes with both A and B. Thank you everyone.